Your business world. Yesterday, today, and tomorrow. Powered by iBiz Radio.
This is Connie Krauth reporting for iBiz Radio. The following podcast was recorded live at the Honeywell Solid State Electronics Center on March 27, 2007. Bruce Omi, Technical Project Leader and High Temperature Electronics Expert, presents Honeywell's High Temperature Electronics. The Honeywell HTMOS product family of specialty integrated circuits is designed to operate reliably at temperatures up to 225 degrees centigrade for 5 years. Bruce presents Honeywell's Silicon on Insulator CMOS technology and manufacturing process, high temperature product features and benefits, and the key markets and applications, including Honeywell's high-temperature components especially developed for the U.S. Department of Energy's Deep Trek project. For more information, please visit the Honeywell website at www.honeywell.com/high-temp or call 1-800-323-8295.
Hi, I'm Bruce Omi, and I'd like to tell you about high-temperature electronics. Integrated circuit technology and components developed by Honeywell capable of reliable operation at temperatures of 250 degrees centigrade and above, far beyond the limits of conventional consumer, industrial, or even military components. I hope this presentation will answer some of your basic questions, such as what are some of the markets and applications for such high-temperature electronics? What capability does Honeywell bring to this field today? What technology and design tools are being brought to bear, and how are these being used to develop new components that are on the horizon? In the near term, these include a high-temperature precision amplifier, a high-temperature field programmable gate array, a high-temperature non-volatile memory, or double EEPROM, an 18-bit precision A to D converter, and multi-chip modules for data acquisition and control. Here we see some of the markets and applications for high-temperature electronics. You may not be aware of it, but the oil and gas industry makes extensive use of electronics downhole to do things like steer the drill string and navigate, to monitor the drilling process and hardware including the drill bit, and to sense temperature, pressure, and other aspects of the formations downhole. This industry is aggressively seeking to extend the temperature capability above 200 degrees C in order to tap new energy resources. High-temperature applications exist in aerospace and defense centered on such new thrusts such as more electric aircraft and more electric tanks. In these applications, high-temperature electronics are needed for electrical power distribution systems, distributed controls, and power modules associated with hybrid gas-electric military vehicles. The geothermal industry has similar requirements to the oil and gas industry, but only going hotter, up to 300 degrees C and even higher. Satellites and space exploration is another mission where extreme temperatures are encountered, and the ability to cool or locate electronics in a low-temperature environment does not exist, or may be severely constrained. Automotive applications for high-temperature electronics include on-engine sensors and controls, brake sensors, and hybrid power modules associated with the new gas-electric hybrid vehicles that are coming out. And there are other high-temperature applications. But in general, you can use your imagination and envision that any application that encounters a high-temperature environment or where active thermal management is employed for the sake of the electronics, these are the types of systems that can benefit from high-temperature electronics. Honeywell comes to these markets as a supplier of high-reliability specialty integrated circuits. These are served from Honeywell Solid State Electronics Center in Plymouth, Minnesota. Markets served include aerospace industry with applications requiring 15-year mission reliability and capability to operate in high radiation environments. It includes high reliability commercial applications such as industrial process controls, medical industry applications, avionics, and IC components for wireless applications. Our high-temperature components are in use today in the oil industry and avionics markets, and our silicon-based precision pressure and magnetic sensors are used in a wide range of applications. Honeywell has a long-standing presence in the high-temperature integrated circuit industry dating back to 1995. Here you see a family of silicon-on-insulator CMOS integrated circuits that are available from our website today. As you can see, we've collected over time over 2 million hours of device and reliability data at high temperature, firmly establishing our capability to provide long-term, 5-year, continuous, reliable operation at temperatures of 225 degrees C or higher. All of the components you see here were designed, fabricated, tested, and screened at Honeywell's Plymouth, Minnesota facility. At Honeywell, high temperature really means wide temperature. Low temperature performance need not be sacrificed in order to achieve high temperature capability. Our technology is capable for operation over an extremely wide temperature range, from minus 55 degrees centigrade to 300 degrees centigrade. This technology includes our silicon-on-insulator CMOS integrated circuit manufacturing process, which has been optimized for wide temperature applications. Design platforms that include simulation models, layout and electrical rules which support this high temperature capability with accurate models that are applicable over this wide temperature range. We have successfully accomplished a number of integrated circuit product designs, and we have magnetic field sensing capability through our magnetoresistive field sensing elements. We have expertise in assembly and test, and our technology is suitable for analog, digital, and mixed signal applications. So how do we do it? At the core of our capability is our silicon-on-insulator integrated circuit manufacturing process. Here we see an illustration showing P and N channel field effect transistors fabricated in a traditional bulk CMOS process on the top and in a silicon-on-insulator process below. In the bulk process, the transistors are electrically isolated from the substrate and from each other by semiconductor p-n junctions. In a silicon-on-insulator process, this electrical isolation is achieved by embedding the transistors in silicon dioxide, essentially glass. Silicon dioxide is an excellent isolation medium, allowing superior packing density, reduced capacitance for higher speed operation and reduced crosstalk, and superior high temperature performance. At this point, you may be asking yourself, what's the big deal? Why don't silicon integrated circuits work at high temperature? There are many factors involved, but the first and biggest issue is the fact that p-n junctions leak. Every active device on an integrated circuit requires p-n junctions. But as we've just seen, a bulk CMOS process involves p-n junction area far beyond that which is associated with active device operation. This is a big problem, because p-n junctions leak or conduct, and this leakage current doubles with every 10 degrees centigrade temperature rise. The solution is to use a silicon-on-insulator process. p-n junction area is thereby reduced to the minimum area required for active device operation. Oxide isolation reduces high temperature leakage by orders of magnitude. The second issue is the fact that the active devices themselves, the field effect transistors, also leak by virtue of subthreshold conduction. This subthreshold conduction also increases with temperature. Because of this, standard commercial silicon-on-insulator processes may not be good candidates for high temperature. These processes are optimized for speed and density, not high temperature, and therefore may leak badly above 150 degrees centigrade. At Honeywell, we have optimized our SOI for high temperature, retargeting the transistor threshold voltage and thereby adjusting the transistor turn-on characteristics in order to manage subthreshold conduction at high temperature. A third issue is electromigration. This is a phenomenon where aluminum used for on-chip power and signal routing actually moves downstream in the direction of current flow. This phenomenon is a very strong function of both temperature and current density in these conductors. We can trade these aspects off against each other. This is done through design rules and layout practice that reduces the average current density in order to gain high temperature reliability, which is done on all of our high temperature products. Here you see some of the important parameters and features of Honeywell's high temperature HTSOI4 integrated circuit process. This is a silicon-on-insulator technology with 0.8 micron transistor dimensions capable of 5-volt operation. This technology is optimized for high temperature performance, employs 4 layers of metal interconnect, and includes features and capabilities for precision analog as well as digital integrated circuits. Putting it all together, Honeywell has integrated high-temperature integrated circuit processing technology with design tools and platforms that are proven by a record of successful designs. This includes the high-temperature silicon-on-insulator process flow optimized for wide operating temperature range. It includes design kits for full custom analog or digital integrated circuit development. These kits support schematic capture, simulation, layout, and design verification using commercial industry CAD tools from Cadence. It includes digital gate array design platforms that have been extended to high temperature in order to implement complex digital integrated circuits from hardware description language netlists. Together, these elements enable development of high temperature mixed signal integrated circuits such as this A to D converter employing over 90,000 logic gates on a gate array platform and incorporating full custom analog blocks on the same die. Recently, Honeywell has been able to team with the U.S. Department of Energy on a project called Deep Trek. The motivation for this program is the fact that much of the remaining U.S. natural gas supply is in deep formations at depths of 20,000 feet and below. And at these depths, high temperatures are encountered, typically in excess of 200 degrees centigrade. This has motivated the U.S. Department of Energy to fund Honeywell to develop integrated circuit components that are capable of reliable operation at 225 degrees C and also capable for withstanding the high vibration and shock environments encountered downhole. Components developed under the Deep Trek project are shown here. This includes a high-temperature precision amplifier. This is a dual amplifier that is continuously auto-zeroed to achieve very low offset and noise performance. It includes a high-temperature field programmable gate array. This is an SRAM-based reprogrammable gate array with capacity for 32,000 logic gates and up to 204 user I/O. It is equivalent to the commercially available Atmel AT6010 part. We also are developing a high-temperature precision 18-bit A to D converter. This is a sigma delta modulator architecture, and it's a complete A to D converter incorporating all of the digital interface, digital filtering, formatting, and serial interface electronics on the same die. It also includes a built-in precision reference and a temperature sensor and auxiliary 8-bit A to D. These features enable simultaneous monitoring of the temperature, which can be digitized at 8-bit resolution and reported simultaneously with the primary sensor input, which is digitized to 18 bits of resolution. And finally, we're also developing a 32K by 8 non-volatile memory, or double EEPROM. We have demonstrated read-write capability at high temperature, and 250 degrees C data retention has been verified using prototype units. This product can be operated as a parallel or a serial memory and incorporates the features and functionality of industry standard 28C256 and 25C256 architectures. In the parallel mode, this product will also incorporate signals for FPGA configuration interface so that this unit can be used to provide non-volatile data storage of configuration data which can be downloaded into the field programmable gate array on power-up or on command. Components developed under the Deep Trek project are enabling Honeywell to address a growing range of needs for high-temperature data acquisition and control systems. Here we see a generic high-temperature control system. This includes means for sensing, signal conditioning, A to D conversion, digital processing, and memory, including non-volatile memory, as well as communications and support functions. We can see how the Deep Trek components fit. Our precision amplifier can serve the sensor signal conditioning application. Our high-temperature 18-bit A to D converter can provide A to D conversion. Digital functions can be served by our high-temperature field programmable gate arrays for capacities up to 32,000 gates of configurable and reprogrammable logic. Even more complex functions can be addressed by our HT2000 gate arrays, providing up to 275,000 gates of logic. Non-volatile memory needs are served by our high-temperature double EEPROM, and other functions are served by pre-existing high-temperature components that are also available from Honeywell. This includes magnetic and pressure sensors, 32K by 8, static SRAM, and other system support functions that are available from Honeywell for high temperature. Going to even higher levels of integration, the U.S. Department of Energy and Honeywell are collaborating on another project to incorporate some of these components in a multi-chip module which will house multiple components in the same package, including all of the interconnect between the devices. In this case, you see a reconfigurable processor for data acquisition that incorporates a high-temperature double EEPROM, a FPGA, and a 32K by 8 SRAM in one package. This package will provide for the user up to 115 programmable I/O at system clock rates up to 10 megahertz. Hardware testing will be complete and prototype deliveries begin in March 2008. In conclusion, Honeywell has been selling commercial high-temperature electronics for over 10 years. And the Deep Track program strengthens Honeywell's high-temperature technology and broadens our product portfolio in a major way. Honeywell and the U.S. Department of Energy are continuing to invest in high-temperature electronics and will be coming out with new components in the future. Bottom line is that silicon-on-insulator CMOS can be used for long-term, 5-year reliable operation at temperatures of 225 degrees C and beyond. And if you need more information, you can visit the website. Thank you.
This podcast is powered by iBiz Radio, a TMA e-marketing company.